Hey, what's up? It's your old pal, Mr. Cook. We just got through the first 8 problems from this review. Now we're starting up on the related rates problems. I'll probably make one video for each problem. So here's number 9. Let's go through it. A 25-foot long ladder is leaning against the wall of a house. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. This is a pretty common type of problem that we've seen. So triangle and ladder, it's, fixed at 25. And then rate of change for how fast it's going away from the wall is going to be 2 feet per second. So that's like in the x direction. So usually when I work on a problem, I always start with like a diagram, and then it's asking us how fast is the top of the ladder moving down the wall when it's base 15 feet from the wall. You've probably seen this a bunch of times. Here's how I tend to do it. If I know that I have the ladder length, I'm looking for like some length like up the wall and away from the wall. I usually make variables for all those values. So the length of the ladder is L. That's going to be fixed. So that's going to offer some nice like things in the future. Going up and down the wall, let's call that the y variable. And then going away from the wall, let's call that the x variable. So once I have all those variables together, I like to, since we're relating the rates together, I like to just write up all of those rates together. So we're seeing how these things change with time. So if I write those up as like rates in calculus, for x, I'd have how much the x value is changing with time, dx dt. I'd have how much the y value is changing with time, so that's dy dt. And then how much the ladder is changing with time, and that's dl dt. And then at a specific moment, the x value is going to be like some distance away from the wall. The y value, the ladder is going to be some distance up the wall. And then L, the ladder is going to be some length. Well, the ladder is never going to change length, so we can just keep that fixed at 25. And then since the ladder is never going to change, we can actually make its dl dt value 0. And it's not going to, that just means that the ladder length doesn't change. Then it says a couple other things, like for example, in this first sentence, the base of the ladder is pulled away at the wall at 2 feet per second. Since it's going away, that means the x value is increasing. So that means that our rate of change is going to be positive. So since moving away from the wall, it'll be a positive 2 feet per second for the rate of change for dx dt. And then, in the last part of the first, question, part A, how fast is the top of the ladder moving down the wall when its base is 15 feet from the wall? When the base is 15 feet from the wall, that's the x value. So that means when x is equal to 15. So 2 things that we need to find, dy dt and also y. And since it says like how fast is the top of the ladder moving down, I'm actually probably looking for this value. In fact, I am looking for, how fast, so rate of change, dy dt, it's going down the wall. But that still kind of leaves this value y, and how do I find it? Because that's like the lone rate and value that I need. And to find that, I'm going to relate these variables together. So if you go back over to the diagram, you see it's a right triangle. And x and y and L are related in the following way. X squared plus y squared is equal to L squared because of the Pythagorean theorem, right? So this will help us to relate any x, y, and L together. And since we have like a specific x and a specific L, we can find a specific y value that relates it. So if I use Pythagorean theorem, 15 squared plus y squared is going to give us L squared, which is 25 squared. And, if you remember your geometry, this is like a 3, 4, 5 triangle. So if you were to solve for y, you'd end up with 20 because it's 3 times 5, 5 times 5, so 4 times 5 would be that other side length. Anyways, so once we have a relationship between the variables and we have all of the rates lined up and we know which ones we're searching for, at this point, we just like plug in after we take the derivative. So we take the derivative using implicit differentiation. The derivative of x squared is going to be 2x dx dt because we're taking its time derivative. The derivative of y squared is going to be 2y dy dt. And the derivative of L squared is going to be 2L dl dt. Okay, so if I start plugging like all of these values in now, okay, all of them, 2x becomes 2 times x, which is 15. Dx dt is going to be 2. The y value is 20. My dy dt is unknown. I don't know what it is. I'm trying to solve it. And then L is 25, so 2 times 25. And this is one of my favorite parts. It's then times dl dt, which is 0. So like this whole part right over here just becomes 0. All right, so let's start cleaning this up a little bit. 2 times 15 times 2, that's going to be 60. 2 times 20 is 40. And then 0 times anything is 0. So then now we just need to solve for dy dt. If we subtract 60 from both sides, 40 dy dt is equal to negative 60. Dividing both sides by 40, we get dy dt is equal to negative 60 over 40. And then that'll reduce down to negative 3 over 2. Okay, so that means that negative 3 over 2 is our answer over here. But if I wrote down just negative 3 over 2, I'd get partial credit, not full credit. I need one more thing, and that's the units, because this is a word problem. Always look for units. And since the rates of change are in terms of feet per second, that's also going to be the case here. So negative 3 over 2 feet per second. Let's make sure that that negative 3 over 2 makes sense, because that's a little weird that we have a negative value, right? Well, remember that the ladder is moving like down the wall. So since it's moving down the wall, the y value may have started up like really high like this, but then at a certain point now it's decreasing. So it's getting smaller. Since the y value is getting smaller as the ladder goes down the wall, that means that dy dt is going to be negative since the y value is decreasing. So that does make sense why we have that. And I just want you to make sure you understand that. If you have a negative rate of change, that's okay. It just means that your y value or whatever variable you're working with is decreasing instead of increasing. Part B says, consider the triangle formed by the side of the house, the ladder, and the ground. Find the rate at which the area of the triangle is changing when the base of the ladder is 7 feet from the wall. So similarly, well, it's actually the same setup. There's a couple of things that we also can keep consistent, like the fact that the ladder is 25 feet. And then let's see, now it's 7 feet from the wall, so that means my x value is 7. And I think also we get to keep that rate of change of 2 feet per second. So that means it's still moving away from the wall at a steady rate of 2 feet per second. So some stuff we don't know. We don't know what the y value is at that point. We can find it in a little bit. And we also don't know its rate of change, so dy dt. But this isn't about like length anymore. It's not about dy dt. We're now trying like bring in another variable, which is the area. So how do I find the area of a triangle? Area, remember, is like 1/2 of the base times the height. So in this case, we make the same variables, x and y. So 1/2 of x times y. So like, I'm going to need these values, dA dt, dx dt, and then dy dt, right? Well, I know that dx dt is 2 still, okay? Don't know dy dt. I'm looking for how much the area is changing, so I'm going to find dA dt. And also, like, it's helpful to know, like, at a specific moment. I know that, like, if we're talking about when x is equal to 7, right? If I know that side is 25, I can find this y value because it's still a right triangle. So I can use Pythagorean theorem again. 7 squared plus y squared is equal to 25 squared. So this is a 7, 24, 25 triangle. So 24 would be that side length over there. So I actually do know like the y value for this. Y is going to be 24 when x is equal to 7. But I still don't know the area. Well, I mean, I can find the area now since I know, I guess, that x is 7 and y is 24. If I, multiply those together, 1/2 of 24 is 12. 12 times 7 is going to be 84. So I get 84 for my area if I need it. So now that I like have all this information, I'm still missing like one thing, and that's the dy dt right there, right? So that's something that I'm going to need to find and plug in. And I'm going to need it because if I do implicit differentiation on this area to find dA dt, here's what I end up with. The derivative of area is dA dt. And then this is like a product rule thing, right, with 1/2 x and also this y. So when I do product rule for it, the derivative of 1/2 of x is going to be 1/2 of dx dt if I take a time derivative times y. And then derivative of y is just going to be dy dt. So I get 1/2 of x and then dy dt, again, from the product rule. So like if I start to plug some of this stuff in, I want dA dt. That's like my goal. So if I plug in some of the stuff I know that dx dt is going to be 2. I know my y value is 24. I know that my x value is going to be 7. But I still don't know dy dt. And the way that I'm going to find dy dt, and this is very much advantageous, of working on part A first, I can actually find it like from a previous problem, the previous problem I just worked on. That's this part. See, they're all related to each other, and they're still related in the exact same way because it's a right triangle. So if I need to find dy dt, I just kind of reset this problem and solve it again. So the x value, if you remember, is 7 now. Dx dt is still 2. My y value is now 24. And then dy dt is over here. And 2L is going to be 2 times 25, but then that dL dt is still 0. So that still ends up being a 0. And then if I like solve this stuff out, 2 times 2 times 7 is 28. 2 times 24 is 48. And then if I solve for dy dt, I get 48 dy dt is equal to negative 28. And if I divide both sides by 48, I get dy dt is equal to negative 28 over 48. And those are both divisible by 4. That gives me a negative 7 over 12. So dy dt, the missing thing that I need is negative 7 over 12. So if I plug that into this last part of the equation, negative 7 over 12, I can solve out dA dt. And then this would just be like calculator stuff at this point. Let me see if I can simplify this a little bit. Gosh, let's see. So half of 2 is 1 times 24 is 24. And then let's see, that gives me a negative 7 times 7 is 49 over 2 times 12, which is 24. So whatever that ends up getting, you just round to 3 decimal places. And then the area units are going to be as follows. So since like the X and the Y values, it's kind of implied, but they're in terms of feet. That means that the area is going to be in terms of feet squared. So it's going to be, something feet squared per second. And then let's figure out what that's going to be. I'm going to do this on my calculator real quick. 24 minus 49 over 24. I got like 21.983 or 9583, my bad. And then the 3 repeats, but I'll just leave it at like 4 decimal places. Okay, so there you go. So that's number 9, A and B. Realistically, like I would say that working on, if you like got through number 9A without any problems, that's probably pretty good. If you struggled with part B, it might just be because like it has a lot of weird features to it. Like it's dependent on part A and like all this other kind of stuff. So, that makes sense. But if you really struggle with 9A, that's when you should probably seek some help. If you didn't struggle with it at all, if you got through it, you should pat yourself on the back. You're doing pretty well with the related rates. Okay, so let's move on to the next problem in the next video. So we'll do 10 in the next video, and then we'll do 11 and 12 and all that stuff. Okay, that's it for me for this video. I'm Mr. Cook. If you need my help, come and find me. Otherwise, go find your math teacher, get some help from them. Hope you found this really helpful. I'll see you in the next video. Bye-bye.